Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon or good morning to those of you who still might be over in our Western time zones. This is Victoria Beale with the Ohio LTAP Center, and we are very pleased to be hosting a research results presentation for the Ohio Department of Transportation on investigation of CMV, commercial motor vehicle related crashes in Ohio work zones. We have with us Melisa Finley, who's a senior research engineer, and she will be making the presentation today. A couple of quick housekeeping items. First off, we are attempting to record this presentation, and if it's successful, we will send out a link to the recording after it concludes. Secondly, we do have a handout for you in the handout section of the GoToWebinar panel. If you can't, for some reason, download it, though, don't worry. We will be sending out a link afterwards in that same email, which hopefully will have a link to the recording. And then last but not least, there is a question box in the GoToWebinar panel. And we would ask that throughout the presentation today, if you have questions for Melisa, please put them in that question box, and those questions will be read to her when she stops periodically throughout the presentation. That's all I have for housekeeping. So Melisa, it's all yours.
Great, thank you so much, and welcome everyone. First of all, I didn't thank you, Victoria, for the introduction for me, but I did just want to acknowledge everyone that contributed to this project as part of our team. You can see here a list of Texas A&M Transportation Institute researchers, as well as our colleagues from the University of Cincinnati who helped us out with the project. Just a quick couple of definitions. I'm going to use some various terminology throughout the presentation, and I just want to make sure that we're all on the same page. So for commercial motor vehicles, or CMVs, I'm basically referring to large trucks or buses with a gross vehicle weight or gross combination weight of more than 10,000 pounds. When we're talking about work zones, we're talking about anything where construction, maintenance, or utility is occurring. I will be mentioning construction vehicles, especially when we start talking about the access egress points, how they come and go from the work zone itself. And when I say construction vehicles, I'm really referring to large trucks or CMVs that deliver materials, haul away those materials, or both. I realize that pickup trucks and other kind of vehicles go in and out of there, but our focus was on the construction vehicles because they're the CMV portion that goes in and out. And then again, a workspace access point is that location where maybe there's a break in the barrier or just a bigger, larger section of the drums where those construction vehicles can come in and out and access that work zone. So just to kind of kick it off, I wanted to tell you a little bit about from the national perspective. This graph is showing the number of CMV involved fatal work zone crashes and the percent of CMV involvement in fatal work zone crashes from 2013 to 2022. You can see that in general, that trend has been increasing for the number of fatal crashes. It did decrease in 2022, and we hope when the 2023 numbers comes out that we continue to see that declining, but we don't know just yet. But you can also see that over the 10-year period shown here in the graph, the percentage of CMV involvement in fatal work zone crashes has stayed relatively constant, between 27 and 34%. Just as a comparison, for non-work zone fatal crashes with CMVs, that's about 10 to 13%. So a lot of times you'll hear in various presentations about CMV involvement in work zone crashes being overrepresented, and that's why, because it's happening more in work zones percentage-wise, a higher percentage-wise than in non-work zones. There are lots of possible reasons for this. A lot of times we talk about there's just more work zones on roadways where CMVs are traveling. We look sometimes at the design elements that we have in work zones. We suspect, because we design those a lot of times for passenger cars, maybe the reduction in shoulder width or lane width or the way we design our lane shifts or crossovers may have some impact on that. We also, again, know that there are just physical CMVs, more of them in that area because they're delivering the materials. And then, of course, we can talk about various driver behaviors or distractions. So there's a lot of, hypothesis and discussion and anecdotally, and to some extent, we're going to talk about today some research to show it, But logically, we can think of reasons, but it's really that question is, can we hone in and do a deeper dive to get more specific on what those types of situations may be impacting CMV safety in work zones? And that's what we tried to do with this project. So here's the goals and objectives for the project. Overall, Ohio DOT wanted to look at improving the safety of CMVs going through work zones. And you can see here the various objectives, and we're going to speak to those as the part of the tasks for the projects. But basically trying to look at what the trends are, what the factors are influencing, specifically trying to determine what the impact is with the construction vehicle access points. It's been talked about a lot on the national kind of perspective and scale lately, and so Ohio just want to take a deeper dive into what actually is going on around those types of locations. And then we developed some recommendations based on all the research. So just real quick, high-level literature review summary. Several studies have been conducted in other states that also show there's an overrepresentation of CMVs in work zone crashes. Rear-end crashes tend to be the primary manner of collision, especially on freeways, for CMV-involved work zone crashes. A lot of contributing factors are listed here on the screen. Again, some of those backed up with actual crash data, some of those trying to look more at a deeper dive into what's going on. Intuitively, we know lane closures can result in vehicle use. We know those then can be a contributing factor to those rear-end collisions. But we also have late or forced merges or lane changes that also can, lead to rear ends or side crashes. Again, we mentioned the construction vehicles entering the travel lanes, various different lane configurations. We're aware that we changed the alignment in our work zones and what impact that has. Surface conditions can also be degraded in our work zones and contribute, as well, again, as various types of driver behaviors. And that can be from speeding to following too closely, distracted driving, impaired driving, etc. So that was all kind of, we did a summary of what existing literature, and then again, we wanted to do some deep dives in Ohio. I just wanted to mention that the Work Zone Information Clearinghouse does have a lot of documents, references, guides, studies about CMV safety in work zones. You can access it at the bottom of the screen. There is the main URL address, and then there is a page for CMV safety. This is just a snapshot of some of the various guides that have been developed to look at CMV, and then a couple specific to large trucks. I did want to highlight more recently in 2023, FHWA, FMCSA, and NHTSA released a commercial vehicle safety and work zones targeted action plan. That's available, as well as a couple of new fact sheets. One looking at providing in-cab traffic-related warning messages to CMVs, and one looking at improving CMVs' ability to navigate work zone lane shifts. So if you're not aware of those documents or you haven't checked out that part of the site, I suggest that you go there because there's a lot of good literature there that I don't have time to go through this today. So what I want to focus on today is really the two pillars, and the first pillar kind of has two pieces to it. We basically looked at a detailed crash analysis, and then we also did some field studies. I'm going to give you a high-level, one-slide overview of the preliminary crash analysis we did early on in the project, just to kind of set the stage and have discussions with the Ohio DOT panel. Then we embarked on a larger, more comprehensive crash analysis that involved a detailed review of crash narratives and statistical analysis, and then we did some field studies at those construction vehicle access points to really observe the operational and potential safety impacts. So I'm going to jump right into the preliminary crash analysis. Large scale, what we did is we acquired the crash data for the latest 5 years. At the time we began this project, those latest 5 years was 2017 to 2021. We also obtained information on roadway inventory. We wanted to look at general trends for non-CMV involved and CMV involved work zone and non-work zone crashes. So basically wanted to compare and see where there were issues, like looking at that overrepresentation of what was going on. We computed some general descriptive statistics for those and compared those. So overall, just so you know, for Ohio specific, work zone crashes comprise about 2% of the total crashes, and less than 1% of the total crashes involved a CMV in a work zone. There were higher percentages of sideswipe passing injury crashes and rear end fatal crashes in work zones compared to non-work zones when you're talking about CMV involvement. About 2/3 of the CMV involved work zone crashes occurred in the activity area, and about half of those happened when a lane closure was present. While most of the lane closure related CMV involved work zone crashes occurred in the activity area, a quarter of them took place in the transition area, so that's where you're starting to merge, and a 15% happened in advance of the warning area or before the warning sign, the first warning signs. So you start to see a hint of possibly that queuing being involved just from looking at the data and where those crashes are happening relative to some of the variables that are in the crash data, like work zone location and type of work. So using that kind of first snapshot, again, we wanted to move into a more comprehensive crash analysis. For this, we focused on KAB crashes, which are those fatalities and major and minor suspected injury crashes. We wanted to basically do a deep dive into the crash narratives and diagrams. So not only using the variables that are available in the Ohio Crash Database, but wanting to look in to those narratives and diagrams to get a better idea of what were some of the reasons, maybe documented from a work zone perspective, of what was going on and contributed to those crashes. We wanted to know specifically, did the crash involve a CMV? And so there is a flag in the Ohio Crash Database. We have seen in some other states maybe where that flag isn't 100% accurate all the time. And so we wanted to double check the narratives, the diagrams, the actual crash reports, and make sure that it was a commercial motor vehicle of how we were defining it, a large truck or bus of that 10,000 pounds or more. We also wanted to see if the CMV was the one that was labeled as being at fault. We also wanted to look at the description of the vehicles and figure out if it was a work-related commercial motor vehicle or not. And then we also developed a table that you can see here. It morphed over time. We had some larger categories to begin with, and then we condensed them down and aggregated them into the categories that are listed here, about the factor that primarily influenced the crash. Now, this is kind of separate than maybe what you see a lot from the speeding or, driver behavior, distraction, those pieces. We were really trying to figure out what of the work zone was the contributing factor. Now, that said, there are some here that do represent a couple of driving behaviors because those rose to the top. But we really wanted to do a deeper dive, and if we could figure out something work zone related that seemed to be the primary influencing factor for the crash, organize that and categorize that so we could look at it. And then we used 2 statistical modeling techniques. I am going to mention them today as I go through the data. I'm not going to spend a lot of detailed discussion on it. Once the report is published, if that is something that interests you, you can get into those details, but we did use the 2 statistical analysis modeling techniques that are on the screen here. And again, I will briefly mention how those analysis methods supported our findings. So overall, here is a snapshot. Again, there's going to be a lot more details in the appendices of the final report once it's published, but this kind of gives you a snapshot of the key findings from the KAB crash analysis. And this is just, again, I don't know if I mentioned it or not, but CMV involved work zone crashes. So I did briefly here in this table, because in the final report, we do separate out for the second analysis ODOT maintained roadways and non-ODOT maintained roadways. So I give a little glimpse of that here today. I'll briefly mention some differences for the non-ODOT maintained roadways because some of those folks may be online. But again, if you want more details for that, that will be provided in the final report. So a couple of things to mention about the ODOT maintained findings is we see of the KAB CMV involved work zone crashes, about 83% occurred on freeways. 54% of those were in urban areas and 29% were in rural areas. We also see across the board that the CMV was at fault about 56% of the time. We do see the percent that a work-related CMV was involved being a little lower on the ODOT maintained roadways. The most common causes, so if you remember that quick table I just showed you on the last slide, we organized and categorized again, and we came up with the most common causes of maneuvers and things that were happening in the work zone that were the result. And this was supported again by the statistical analysis as well. Queuing was across the board the most common cause. We also saw lane departures. And then for ODOT maintained roadways and overall, we saw lane changing. So this is one where there's one difference on non-ODOT maintained roadways. The third most common cause on those roadways was actually intrusions into stationary work zones, which may explain why there was a larger percentage of work-related CMVs involved, because in most times when we're reviewing those crashes, a vehicle would hit some kind of, CMV large truck that was parked in the work zone, most notably the truck mounted attenuator on a, shadow or protection kind of truck. You can also see the percent that were attributed to construction vehicles entering or exiting the workspace. And actually it was a small percentage, only 2% on ODOT maintained roadways, a little higher, just a couple of percentage on non-ODOT, and then 3% overall. So we're going to take a moment and do a deep dive, a little bit deeper dive, based on the time that we have together, into the top 3 common causes for the ODOT maintained roadways. And again, I'll briefly mention if there's any differences for the non-ODOTs, but those details will be in the final report. So there was 121 queuing related KAB CMV involved work zone crashes on the ODOT maintained roadways. 54% of those occurred in an urban area, so slightly more than half. And you can see here, one of the eye openers is that 94% of them were rear-end collisions, as expected when you have queues and slowing down traffic. A CMV was at fault in 65% of these crashes, and more than half occurred when a lane closure was present. So again, tying that reduced capacity into the slowdown and resulting in those rear-end crashes. To note, compared to the non-ODOT maintained roadways, the findings were very similar, except there were more queuing related crashes in rural areas, and that number was 60%. So for the ODOT maintained roadways, we see that 26% of the slowdowns that were associated with lane closures happened in advance of the warning area or before the first sign. So this is starting to indicate that our queues are backing up outside of the work zone, where motorists may not be aware that, one, a work zone is happening further downstream, or be expecting that sudden slowdown. Queuing because of lane closures, though, also caused crashes in the activity area and in the transition area. So we see them happening in other places as well, but the primary location, or the largest, was in the advanced area or before the first sign. The statistical analysis modeling techniques that we used did support these types of percentage, or the fact that queuing is a primary contributing factor. 43% of the crashes were associated on freeways and expressways with reduced capacity due to lane closures and the result of rear-end crashes that came out of that analysis. So it was the top cluster analysis that we did. The largest proportion of the crashes were connected with this queuing related behavior and these sudden slowdowns. We did see, other than lane closures, that queue-related crashes happened when there was also work on the shoulder or median. Some of them also resulted from lane shifts and crossover work, as well as mobile work, which we can understand the mobile work, a smaller percentage, about 7%, because it also reduces capacity. But shoulder or median work can reduce, especially if you have barrier up against the lanes. There's reasons why people may have slowdowns, also in lane shifts and crossovers, maybe because of the design of those in the need to be able to maintain your lane. So it's not just lane closures, even though lane closures was the largest proportion. So because we were seeing so many crashes still associated with queuing, sudden slowdowns, and lane closures, and having discussions with the ODOT panel and knowing that there were lots of existing policies, procedures in place, one, the permitted lane closure system, as well as their MOT exception policy, they ask us to do a deep dive into the queuing related crashes to really try to see and glean as much information as we could. And so what we did is we matched each crash to a past project using data from ODOT's Transportation Information Mapping System. We also reviewed ODOT's traffic management and work zone exceptions database to determine whether each project attained an MOT exception. We reviewed project plans, addenda files, and bid data to determine if a work zone queue detection warning system was used. And we also reviewed daily diaries to obtain insights about temporary traffic control at the time of the crash for the top 10 projects. So the table that I'm showing here shows that we could match successfully 108 of crashes to projects out of the 121. And then you can see there were several projects that had multiple queuing related crashes. And so we took a look, I'll talk about it on the next slide, but we also took a look more at the top 10 projects. But basically it shows here on the screen that there was some MOT exceptions that were provided for several of these projects. You can see the variety of exceptions that were allowed. Many of them including lane closures or ramp closures, some of them including the closure of one direction of travel, 3 doing a complete road closure and detour, and then 1 using a crossover. 3 of the projects also we found documentation for where they were using those work zone queue detection warning systems. So since, again, several of them did have MOT exceptions, the panel asked us to do that deeper dive into the top 10 to try to look at, the question of basically, was an exception allowed, yet we still saw crashes? Was one not accepted? Was the lane closure during the permitted or allowable time? Again, just trying to get insights into what was going on so that we could help make recommendations to further improve policies as needed. So we looked at those top 10 projects, dove even deeper into the information, and it revealed that 8% of those the crashes occurred when a lane closure was present, but was not permitted by any of the documentation. So that was whether or not it was, when it wasn't permitted by the lane closure schedule, the plans, because sometimes the plans based on the impact analysis had additional time frames when they could not have a lane closure present, and then also whether or not they had received an MOT exception and whether that was for that. So we did find that some of the crashes were related to lane closures that probably shouldn't have been there in place. We also did see some crashes, 29% actually, a little larger, when the lane closure was active and it was permitted or an MOT exception was allowed. And so, this really starts to ask the question of, what else needs to be done to be involved with the initial work zone impact analysis, a more detailed one as you get closer into the MOT exception process, to make sure that the exceptions that you're allowing are the current permitting lane closure system is accurately reflecting what's happening on the roadway. And so I think this was kind of eye-opening for all of us, is just knowing that there may need to be some tweaks done in the future to better capture what's going on. It's all estimates. We try to do the best, but being able to continually and proactively look at these types of data sets lets us then reflect and look at what maybe we can improve to reduce those numbers. We also saw 29% was when shoulder or median work was going on. So nothing in the diaries, nothing in the plan set, the phasing that was going on really hinted at there being a lane closure present. It seemed that the work was off the side of the roadway, so the reason for the slowdown wasn't as apparent. And then we did again see that 6% that was involved in a lane shift or a crossover. So again, anticipating several of the narratives actually mentioned, or the diaries would mention that a crash had happened, and it would note something that was going on. And a lane shift or crossover was specifically mentioned in a few of those as well. So it was good to see that, to be able to confirm what we had been seeing in the other analysis. And again, this is a deeper dive of a handful of projects just because of the time that it takes to do it. But it did give us some additional insights that we didn't have, even just from the more comprehensive crash analysis and the statistical analysis that we did to support that. So also we wanted to look at the lane departure related crashes. That was the second most common cause on the ODOT maintained roadways. And here again, we see that these crashes occurred most in urban areas. A CMV was at fault in about 68% of these crashes, but a work-related CMV was only involved in about 5% of the crashes. The most prevalent crash types for the lane departure related crashes were fixed object and sideswipe passing. So when we reviewed the crash narratives, we determined that about 2/3 of the lane departure related KAB CMV involved work run crashes on those ODOT maintained roadways were a vehicle that left the roadway. So completely not just left the lane, but left the roadway. 1/3 of them were vehicles that just left their lane. So they drifted out of their lane, they swerved out of their lane, or they crossed over into another travel lane when they were not changing lanes. So that was a separate category, that the lane changing was separate from lane departure. 41% of the lane departure related crashes occurred when there was work on the shoulder or median, 23% when there was a lane closure, and 22% when there was a lane shift or a crossover. And then again, a smaller percentage, about 8%, for intermittent or moving work. Most of the crashes did occur in the activity area. And so we didn't have that was about 73%. So we did not have as many upstream like we did with the queuing type of crashes that are associated with those sudden slowdowns. Just as a nugget of information, we found similar trends for the non-ODOT maintained roadways, except more lane departure related crashes occurred in rural areas, and that was about 59%, and during intermittent or moving work, and so that jumped up to 67%. I did forget to mention earlier, and I apologize for that, but the non-ODOT maintained roadways does include the turnpike roadways. And a large portion of them were the turnpike facilities, so freeway crashes as well. Only a small portion were different types of roadways. So we have the exact breakdown and data for that in the report if you're interested, but I should have mentioned that earlier. The statistical analysis that we did found this again to be the second largest cluster, so it kind of went along with our narratives analysis matched with our statistical analysis. Were associated with driver behavior related to sideswipe passing and run off the road crashes. Factors from the statistical analysis included work on the shoulder or median, vehicles moving at unsafe speeds, primarily freeway and interstate routes, roadway curvature, crashes with fixed objects, and the presence of a work zone lane shift or crossover. So again, what we were seeing and reading from and putting together some descriptive statistics from the narrative analysis, simultaneously running the larger data set through the modeling, we were confirming and validating that we were seeing the same thing, and these two analyses were complementing each other. So the last group I want to talk about today is the lane change related crashes. This was the third most common cause on the ODOT maintained roadways. Now this is a vehicle changing lanes, but not because of merging due to a lane reduction or closure. We kept those separately. So we had lane closure merging as a separate category, and we had just regular lane changing as a separate category. We did that because we wanted to be able to see the differences between just lane changing behavior in a work zone and then between having to merge because of a loss of capacity. So again, the lane change crashes happen most often in urban areas. We see a larger shift to urban here with 82%. The CMVs were at fault in about 64% of these crashes, but a work-related CMV was only involved in about 7%. The most prevalent crash type was side swipe passing collisions at 90%. 46% of the lane change related crashes occurred when there was work on the shoulder or median, 21% when there was a lane shift or crossover, 16% during a lane closure, and 8% during that intermittent or moving work. Most of the crashes, again, occurred in the activity area. So for this specific category, there wasn't a lot of details about the work zone conditions and the crash narratives, like there was for some for the lane departure, but especially for the queuing crashes. There was a lot more details in most cases about the work zone conditions. It mentioned queuing, it would mention whether there was a lane closure, etc. But for these, it got a little bit more light on anything that we could glean specifically. But from the statistical analysis, that same cluster of crashes did again the one that I just talked about that had sideswipe and run off the road crashes was correlated with lane change behavior as well and the presence of work on the shoulder or median. So we saw that fall out of a very similar cluster in our analysis. A lot of times improper lane changing can lead to vehicle conflicts, which can be the resultant of that side swipe passing crashes in the activity area, especially if it's tight, physically constrained. If you've removed shoulders or reduced shoulders, maybe you've reduced lane width. But again, unfortunately, we weren't able to obtain those types of information specifically and have that historical specific work zone information to be able to match back with these crashes. So a lot of that, again, is just kind of anecdotal or intuitive about what might be happening related to this grouping of crashes. Real quick, just wanted to talk about the construction vehicle ingress and crashes. 2% again, where the ODOT maintained. Interestingly, 70% resulted when a vehicle was exiting the workspace. 90% involved the construction vehicle. You may ask, well, what about the other 10%? Those were crashes that in the narrative, it mentioned the construction vehicle exiting, but they were involved in the crash, but they caused some kind of jockeying, lane changing, sudden slowdown that caused other vehicles to get into a crash. 50% of the time, the construction vehicle was at fault, and then you can see here it was an even split between rear end and side swept crashes. So I'm going to pause there and see if we have any questions about the crash study. Maybe a couple of them I could address right now, and then we'll dive quickly into the field study part of it.
Sounds good. We do have two questions. The first one is, excuse me, by work-related CMV, and work-related CMV was in quotes. Do we mean CMVs from contractors, suppliers on the project for which there is that specific work zone?
Yes.
Okay. Next question. Do we have any stats on if queue-related crashes were more likely and how much more during lane closures not being permitted under the PLCS?
So we just have that information for those top 10 projects. We only looked at 10 projects just because that was a heavier lift and something that we kind of tapped on near the end of the project just because we were asking a lot of questions about the queue-related crashes even after doing the deeper dive and the statistical analysis. So I don't overall have some kind of number for that. It would just be the information that's in the project, the publication about those 10 projects. So the percentages I put up there on the one slide were just coming from those 10 projects, not even the 108 crashes, just the, I forget how many crashes it represented, but it was the top in the little table, the top 10 projects that were there.
Great. And then one more quick question. Someone wanted to know, did you address weather or night versus day in your analysis?
There is some night versus day in our analysis. It's in the details. I'm sorry I didn't get into that today, but there is some information about night and day. Weather was one of the categories I showed in the table. It didn't play a large factor, but it is mentioned, and there's details about that in the report.
Great, we're good. Thank you.
All right. So the field study, what we did is we looked at 3 work zones. So we worked with the panel, we looked at several different projects that were ongoing during our time frame, and we landed on 3 projects. And you can see them here on the map. Here is a listing, I won't read them all, of the various things that we collected near and around the workspace access points. And I'm going to go through a high-level overview of the findings for these types of field data that we collected. We give you a snapshot of about 606 hours of video that we had pointed at various workspace access points to watch the interactions between work-related CMVs entering and exiting the workspace and the vehicle in the open travel lanes. We ended up observing a little over 1,300 construction vehicles across all 3 projects. I will say that most of our data reduction and analysis focused on the light blue work zone that was on I-71, mainly because it had upwards of, I think at one time, 10 workspace access points. It was a really long project, so we could just collect a lot more data at that project at different workspace access points over the time that we had a video trailer at that location. Specifically at that location, there was 1,271 of the construction vehicles. So you can see how much that project played into our data set size. These are the things from the data we collected that we analyzed. We compared the workspace access point designs to the ODOT standard construction drawing, which is the MT 103.10. We reviewed the construction vehicles entry and exit paths, and we actually organized them into 10 categories. I'll go into a little bit more details on that in a minute. We computed post-encroachment time as well as the time gap between construction vehicles entering and exiting and the vehicles immediately following or before. And I'll go into some details about that and how we did that. And we used that as a surrogate safety measure. And then we also looked at the speed of the trucks themselves, decelerating and accelerating. We computed collected some, computed the average speed data for the main lane traffic to give us an idea. We talk a lot about speed differentials when large CMVs are coming in and out of the work zones. So we wanted to actually capture that and have some quantitative numbers to associate with that. And then we looked at lane change behavior and also computed some volumes. So I don't have time to go into deep details on everything today, but I am going to try to give you a snapshot and a sneak peek to hopefully heighten your desire to want to go check out the report and get more details. So this is a quick drawing of kind of the post-encroachment time methodology that we used as a surrogate safety measure. Traditionally, this is looked at a lot at intersections, but we found a couple of literature papers about looking at it and using it for emerging behaviors, and we adapted that to our situation. The research team, we calculated 1 to 4 PETs for each construction vehicle, dependent on whether it was entering or exiting and whether it exited and stayed in the inside lane or immediately kind of went over into the outside lane. Most of these were 2-lane in each direction type facilities. So for those that were entering, basically as soon as the truck would leave the main lanes and enter into the designated lane that's used in the construction drawing standard, we would say that that's where the line was. And then we would calculate the time back to when the next vehicle passed. So the trucks entering the work zone was a fairly simple calculation. For those exiting, it was a little bit more detailed. We had to look at when the vehicle first started to enter the inside lane. All of these workspace access points were in the median. And so these were trucks entering into the inside or fast lane. And then we would basically look at the video and compute the difference between the car that was coming behind the truck that just exited, and then we would back up the video, and when the car that was immediately before the truck crossed what we called the invasion line, we would then look at that time as well. And so for the trucks exiting, we could actually build a gap time. What was the gap they took before the leading and the following vehicles when they were exiting the work zone? And there's a lot more details about how we computed everything, again, in the report. The final data set contained about 352 construction vehicles and 507 post-encroachment times. Sometimes, depending on where we could put the video trailer, depending on where and how they were accessing the work zone, we couldn't use all of our video for the PET computations. So that's why it's less vehicles than I mentioned earlier overall. So just real quickly from the workspace access point design, this is a snippet or excerpt from the standard that Ohio DOT uses, just to kind of show you if you're not familiar. Trucks are supposed to come in and decelerate in the designated lane that is outside of the main travel lanes and enter into opening A. When they exit, they come out of opening B and then use the dedicated area to accelerate and then merge with traffic. We found that most of the workspace access points implemented were according to the standard. We did observe a couple of instances where they were used differently than what I just described to facilitate material delivery, and I'll show you kind of that in a second. And then we also observed other types of workspace access point design. So we did see some that we call like slip entries, which were at the beginning or end of a work zone, where they would basically just use the inside shoulder or maybe some added pavement to get off and exit in, or vice versa, exit out at the end of the work zone. And then occasionally we did see some of the contractors using some of the U-turn turnarounds to facilitate the trucks being able to more quickly access the opposite direction of travel. But most often the construction vehicle drivers use the dedicated lane as intended, and you can see that here. So this is just a drawing kind of showing that concept of opening A and opening B. These are for construction vehicles that were decelerating and entering into the workspace. What ODOT would like, and is according to a note on the standard, is vehicle path number 1, which you see about 2/3 of the trucks did. And that is using as much of that deceleration lane as possible and not decelerating necessarily in the travel lane itself. But you can see some trucks would basically, the 2 represents they went halfway down the deceleration lane. That was kind of our line in the sand where we kind of made a difference between number 1 and number 2 paths. And then number 3, you can see, was one of those that was facilitating material delivery. They couldn't access any other way, and so they actually would come in and then back into that entry. Just real quickly, I think what is interesting is these deceleration profiles. These are fully loaded dump trucks, about 30 of them that we were able to get their speed profiles. They actually start decelerating in the inside travel lane about 400 to 800 foot before they enter the dedicated lane. So what you're seeing here, the 0 point, is that opening A. So from opening A, it's about 800 to 1200 foot upstream. But once where the dedicated lane is, it's about 400 to 800 foot upstream of that. So they are still using that main lane to decelerate. Their initial average speed was 55 miles an hour. It ranged from 41 to 62. And their average speed when they entered the dedicated lane was about 43 miles an hour and ranged from 29 to 59 miles an hour. Interestingly, the vehicles in the main lanes were traveling on average about 66 miles an hour in the area, and the posted speed limit was 60. So what did that result in? Basically, it resulted in lane changes as expected. We were able to look at lane changes surrounding about 200 construction vehicles. You can see it averaged out to be about 1 lane change per construction vehicle, with about 3/4 of them moving from the inside lane to the outside lane as we'd want. Occasionally, unfortunately, we did still have people move the opposite direction. That just kind of depended on traffic and what was going on. But you can see here that 43% of those were classified as last-minute lane changes, which means they got fairly close to the back of the truck before they were making a last-minute lane change into that opposite lane. From the post-encroachment time findings, we were able to compute that it was about 3.3 seconds behind was the average of how far the vehicle was behind. And then you can see the range and the standard deviation here. We also had the construction vehicles that exited the standard design that ODOT has. Here, number 5 would be the path that is noted and encouraged on the standard sheet. Again, that's using most of the dedicated lane to accelerate. The number 4 path would be folks, drivers that entered the main lane traffic before the halfway point of the designated lane lengths. And we can see almost 60% were using the desired path, but almost 1/4 were using getting over maybe a little earlier. Now that could be because traffic was light, right? And volumes were light. Again, we have detailed volume data in the final publication, but we did see drivers doing maneuver 4, 6, and 7 more when the traffic volume was light and they had the ability to go ahead and take that gap. And then you can see some unique uses of opening A as well. So we again have the acceleration profiles for these trucks, which I thought was very eye-opening. We did some empty dump trucks as well as fully loaded dump trucks. 19 empty, 32 fully loaded. You may be asking why it starts at 10 miles an hour in these graphs. That's because the equipment that we use does not register below 10 miles an hour. So they usually came up to the opening B gap, would stop most of the times, kind of gauge what kind of gap they could find in traffic, and then go. So they did start most times from 0. We just couldn't capture between 0 and 10 miles an hour. The average speed of the empty dump trucks when they entered the travel lane was 42 miles an hour. The average speed for the fully loaded trucks was 27 miles an hour. And in this vicinity, during the time that we were collecting this similar data, the average travel speeds was about 69 miles an hour, again with a posted speed limit of 60. So you can really start to see that speed differential come to life on these trucks that are trying to accelerate and enter. Obviously, there's a large difference between 27 and 69 miles an hour. Slightly less difference between 42 and 69, but again, before now, and lots of the conversations I had in national workshops and stakeholder events, you know, we knew there was a speed differential, but really didn't have some data to show exactly what that was. So with those slower trucks entering, we also looked at lane changes. We see here 81% moved from the inside lane to the outside lane. And we did see 28% last minute lane changes. So less last minute lane changes with the trucks entering than exiting. I think that's because you could see the trucks utilizing the dedicated lane, so people had more time to get over. We see a higher percentage moving from the inside to the outside lane. We also see that with the gap. Here's the PET findings. I went ahead and broke it out by the following vehicle. We see a larger PET of about 5.8 compared to that 3.3 for the exiting vehicle, for the entering trucks, the ones that were exiting the main lanes. And then we obviously see the leading gap too. So basically about 15 seconds was the gap that the trucks were taking. Now, that said, 15 seconds doesn't last long when you have large speed differentials, but wanted to be able to provide that data to you, and there's some more information here. There's a lot more details in the appendices. We break it actually, all the PET findings down by vehicle path that I showed you earlier. Here, I'm just showing you the overall data and not particularly honing in on one type of vehicle path. I'm going to take a break there and ask if there's any questions on the field studies, and then I can go through with the remaining of our time what our recommendations were.
No questions at this time.
Okay. So the recommendations, we had 10 of them in total. The first was to monitor the implementation of the new permitted lane closure schedule that was made available in February of 24. So you might have noticed our crash data was older than that, and that was because of when we started the project and what was available at the time. So we're aware that some of those deeper dives that we did and some of the projects that we had were for the previous system. And so we just think that it would be, that ODOT continue to monitor, especially looking at, maybe doing some deeper dives, looking at the risk, following those ones that get the MOT exceptions, and making sure that, what's happening in those when they're allowing those exceptions, et cetera, and seeing how the new permitted lane closure schedule is working with respect to the capacity issues that we may have seen on some of the projects, that their allowable times for lane closures may change based on the new system. We also think that they should closely monitor projects. Oh, I just missed that with the approved MOT. So I'm sorry, I jumped ahead of myself in the last one. But basically, that's why when we were seeing some of those, we saw some crashes with MOT exceptions and some without. And so closely monitoring them, maybe there's some reports that can be done or auto-generated to help more closely follow those ones that are given MOT exceptions. But I do think with the permanent lane closure schedule, it's also looking at those ones that, are following the schedule, but if for some reason safety issues start to arise, really maybe doing a deeper dive on that project to see what may have been permitted, but what's actually happening in the field, and then see if there's, improvements that can be made there to those kind of calculations. And based on that, we suggested maybe using other data-driven performance metrics when lane closures are allowed. So right now, a lot of the basis is on the queue length based on available capacity versus the demand or traffic volumes. We've seen where sensitivity analysis can really provide additional insights into potential impacts, especially for projects that may need those MOT exceptions. Sensitivity analysis can include variations in traffic volumes, including passenger cars and CMVs, introducing trying to compute the likelihood that a queue will occur, almost like the probability. So if, for instance, it's not just a yes, no kind of question. It's if I slid this by an hour or I moved it this way a little bit, what's my sensitivity with traffic volumes to know the probability that a queue will occur and how long it will last. So it may be that you have a queue, but it's only going to last 30 minutes. But then on the other end of it, you could look at it and say, hey, I'm going to have a queue and it's going to last for several hours, even, and the probability of that queue forming is very high. And so it's just trying to use some more information to give some details that may help with some of those projects that are on the cusp of needing those MOT exceptions or other additional details for the queue closure analysis tool. We talked about developing some criteria-based tool for the work zone queue detection warning system. Again, several of the projects had queue warning systems. We couldn't tell, they were paid for. We couldn't tell if they were actually active on the day of the crash or not. But maybe a tool that incorporates specific data-driven scoring factors could be used to help more consistently decide when those types of tools should be used to help mitigate queue end or rear end crashes from queues. We talked a little bit about lane shifts and crossovers and them contributing to the crashes. So just want to reiterate that really those types of geometric changes in alignment should be designed for the operating speed of the roadway before you introduce the work zone. Realizing that can't always happen, but trying to make that a priority just to reduce some of the surprises and things that happen when people are approaching those work zones still at higher speeds. We also talked about considering slightly wider lanes and lane shifts to better accommodate the off-tracking tendencies of CMVs to help them maintain their lane position, thinking of those lane departure crashes that we evaluated. And again, there's a recent fact sheet that references some work that was done by Indiana DOT that I think would be really good for the Ohio folks to look at on how to do that. Pretty simple, low-cost safety tool to use for that. Because of the post-encroachment time results finding, as well as the lane changes and several other things we saw in the field studies with the speed differentials, we recommended that ODOT lengthen the dedicated lane on the construction drawing. There are also several states that have taken Ohio's idea, and they too have longer dedicated lanes. And so when we do some computations, we look at the speed differentials that we had and various results that we had. We made some recommendations on what we think those links should be and gave them to ODOT. We also talked about adding a drawing to that construction standard to really show the way that we'd like construction vehicles to enter and exit. It is a current note on the standard, but some kind of a graphic to show, to encourage them to use the full deceleration area, especially if the deceleration and acceleration lane is lengthened, really trying to get out of the main lane traffic and while you're decelerating and stay in the dedicated area while you're accelerating as long as possible. And then last but not least, we wanted to continue to encourage the use of the work zone egress warning systems that warn approaching drivers about slow moving construction vehicles. We didn't specifically look at those in this project. Other work is going on nationally, looking at those types of ITS systems, but still, again, because of the findings and the results that we saw from the field studies, thought it was a good idea to continue and promote the use of those. And then we also wanted to continue to use law enforcement judiciously in work zones to help encourage speed limit compliance and reduce speed differentials between those slow-moving construction vehicles and high-speed traffic. So those were the 10 recommendations that we had. I think we have about 3 or 4 minutes left if we need to answer any additional questions.
There's a couple. One is they would like to know when the full report will be published and available to the public.
I do not know. The full report, the final report is in the hands of ODOT. I'm not sure how long that typically takes internally for them to do that.
I'll make certain that the research office has a complete list of everyone who is on this webinar so they can notify you when it is published out. The last question we have right now is there a link to the guidance document from Indiana?
There is. I don't have the ability to provide that right now. Is that something we can send out with the email if I give it to you, Victoria, or would you? I can sit here and try to find it.
No, yeah, you can send me the link and I'll send it out with the follow-up email. And then Jennifer, Jennifer has said that she has an answer for us on when the document's going to be published. So Jennifer, if you just want to unmute.
Okay, can you hear me?
We sure can.
Okay, so this project will be posted on the ODOT website within about a month, but it will take some time to get posted at the state and national level. We don't have a time frame for that because they don't give us one, but typically we're like, 4 to 6 months on the state website and then probably about the same on the national website. Anybody can pull it down off of our website as soon as it's published.
Sounds great. Thank you. And I believe that's all we have for today. We're up against our time. So Melisa, we want to thank you very much for a great presentation. And hopefully this information is going to be used to help, lower the number or possibly even eliminate those crashes that are happening. So
thank you again.
Thank you. Everyone have a great rest of your afternoon. Make sure you get out and hopefully enjoy some of the beautiful weather we're having here in Ohio today. Take care.